Okay. Lucky I come early. Every week I struggle with the fight the PC. Okay, very good. So today I'm finally done fighting the PC. Alright, very good morning. So welcome back from your public holiday. I hope that you had a good break. Okay. Alright, so I've got good news for you. There's a new artifact. Okay, it's called the, I didn't come up with this. It's called the Force Crystal Time Warp. Okay, so what it does is this, it unlocks like an achievement, okay, but it's usable. So you can actually use it, and the way you do it is to email your tutor and say you want to use this. Then once you use this, of course it goes away, and you have 1 day extension to any of the future assignments, except for contests. Okay, so the contests are not will not be extended individually, but all the other assignments you can extend by 1 day. Okay, so how do you earn it? Very simple. You go to IVLE and fill out this survey called the PATH survey. So the PATH is actually a new thing that we just introduced this semester. So this is the 4th week, so you have gone through 3 weeks of PATH, and we want to basically do a sanity check to make sure that things are okay, because there's going to be like 10 more weeks, right? So we want to ensure that all the PATHs are doing well. And what you need to do is to fill out the PATH survey, and then, so these surveys are anonymous. So obviously we don't know who wrote what, but then we can find out who didn't write, who didn't submit. Okay, so you need to fill out by tomorrow, I think, or tonight. You check the announcement. Okay, if you fill up the thing on time, before the deadline, you have this, you unlock the achievement, which is actually useful. Okay, if you don't, then we know you didn't submit, you won't get the achievement. Okay, very simple. Then another thing is this, so we have finally settled most of your scheduling issues. So now I have one more thing to schedule, which is the 1010R, which is the JavaScript class. This one will start probably next week. Okay. This will, I have to talk to Martin about this. Martin is doing this, so I have to talk to him. And it's going to be supposed to be 1 hour class every 2 weeks. Okay, so I need to do the scheduling very soon, so you find a room and everything. I didn't know how many of you are interested. And I need to fill out a survey by tomorrow night. Okay, so what will happen is that based on the results of this survey, right, I will go and schedule a time and a day. If you don't fill out the survey, that's too bad. I find a time or day that doesn't suit you, it's your problem. Okay, so this one is optional. If you are not interested in, if you think that, first of all, some of you are really drowning. Okay, so those of you who are really having a hard time probably don't want to do this. Okay, this is for people who have a lot of free time. Okay, who basically, after doing all the missions, still have a lot of time. Then you can do this. Okay, so today's agenda, this agenda. Okay, we go through some of these things. Okay, before we continue, let's recap from last lecture. Actually, it's 2 lectures ago, right? I forget. Alright, so there's this let special form. Okay, where the form is the following, the let, and then the variables and expressions. Okay. Remember that let is synthetic sugar for lambda applied to some expression. Okay. How many of you understand this? How many of you do not understand this? You don't understand this? Okay. So you will have to go and try this out. Essentially, there are more exercises. But it's quite, this is not that important, because you typically, once you look at let, you will operate on it in a certain way. Okay, this to help you understand why let works the way it works. Okay, and in a few weeks we will talk about this. Right now, so it turns out that one thing about let is this. Remember that if you bind like x to something, y to something x, then the second x is what? It's some outside x, right? Correct. So this can be sometimes a little bit inconvenient, right? So basically we have another synthetic sugar form, which is let star. Okay, let star looks like let. Okay, except that let star is really nested let. Why is this useful? So that the subsequent things depend on the earlier things. Okay, I say again. Now, in let, essentially, because let is lambda, you think about it, right? Let is lambda of all these variables, applied to all these expressions, right? Let is the lambda of the variables applied to all these expressions. So obviously, if expression 2 depends on expression 1, it doesn't really work because expression 2, expression 1, they depend on stuff that's outside here. Okay. Now, if you do let star is all this nested let. So obviously now expression 2 can now depend on expression 1 because it's actually nested inside. Okay. All right. So now I'll take out the clickers. Okay. Last week was really the warm-up week for you and for me, because the clickers was new to me. So today we do a lot more clickers. It turns out, if you don't know already, coming to lesson and clicking stuff actually gives you XP also. You just help me who comes to the lesson, obviously. Okay. So, you got it? Okay. So, does it work? It works, I can see the clicking. Okay. Are we all done? Wait. Hey, you're now click or not? Why is the user feedback? I don't know what this is. Okay, are you ready, yeah? Okay, the answer is what? Answer is 2, Okay, it's ugly like anything, but who is this guy who got 9? Okay, anyway, the 9 guy is obviously wrong. Okay. What? Yeah, it's okay, but anyway, the answer is 2. Thank you very much. Okay, this one, answer is click. What's user feedback? I have no idea what it is also. Okay, you ready? Answer is... Okay, some guys still clueless. Okay, so anyway, the answer obviously is 3 here. Why? Because now, okay, let star essentially means what? Essentially means that x is bound to 3. Okay? And now the y will be bound to x. I'm getting feedback again. This is terrible. Hello? It doesn't happen all the time. Quite nasty. Okay. So this is correct, Okay, next. I'm still getting feedback. Oh, man. Hello, City. Hi, this is Ben Leong in LT15. I need someone to adjust the mic for me. The feedback, I need to reduce the volume. Okay, thanks. All right. Okay, so just to make sure we know where we are now so far. Okay, so we talked about procedural abstraction for the first. This is last week. First 2 weeks we talked about this. Okay. And also I remember we talked about this thing called visual thinking, which really is to just solve the problem from top down, right? So you pretend that you have stuff you don't really have, and then you just write first, and after that you go and write the small little helper procedures. Okay, this is the general idea. All right, then we talk about recursion iteration, right? And recursive processes have what? Deferred operations, right? And iterative processes essentially will use some kind of helper procedure. Okay, it keeps calling it, and then the shape of the execution is normally constant size. Okay, this is a general idea. Again, these 2 things we covered during the first 2 weeks. Last week we talked about higher order procedures, okay, which have either take in procedures as arguments, spit out procedures, okay, which is what you're getting now, right, for your all the curve drawing, right, gospelized. Okay, so this is the general idea. And then the last thing is that we also did stuff whereby we looked at some product and all those higher procedures as a means and fold, right? As a means to abstract common patterns. Okay, so the first 3 weeks we essentially have covered procedural abstraction of higher procedures. Okay, this is the essentially what we're doing there is that we are looking at how you can actually manage complexities for operations. Okay, which means that, small things that on how to actually do stuff. So far we've only been dealing with very simple data, which is just numbers. Okay, but it turns out that in programming classes, typically we always deal with numbers because they're easy. Okay, but in fact in the first assignment we already dealt with pictures. Okay, but at the meantime we mostly numbers. So it turns out life is obviously complicated lah. Right? If all you can do is deal with just simple numbers, you can't get anything done. And so the thing is that we need to figure out how to do more complicated stuff. Okay? So to do this, essentially what we need to do is to be able to model real objects. Okay? Because in life, the whole point of computer systems is to actually figure out how to model and manage this sort of models for real objects. Okay? For example, right, the registrar has a record of every student here, even the NUS high students. So there is somewhere, I think we have this thing called ISIS or something like that, right? Which manages your data. Obviously, exam day comes, it doesn't quite work, but mostly it works okay. And all of you have a record inside, okay? So typically it contains, oh no, not too low. Hello? Hello? Yeah, but now my volume was turned off. Too low. Higher. Sorry, now higher a bit. Sorry. This is a real fun thing. Every Wednesday we do this thing. Hello? No, higher a bit. Can I be too high? Can I be too low? Hello? Okay. Hello? Low a bit. Yeah, this is life, man. So life is complicated. Hello? Okay, good. Thank you. All right, so every student has a record that has stuff like info, modules taken, grades. All right, and then the record can, okay, in the past, typically it might be some kind of a paper folder, right? But today, obviously, everything is electronic, okay? So the interesting thing about record is that although each one of you has a record, right, it consists of many small little things, okay? So we call this compound data, which is really like bigger aggregate data consisting of small little simple primitive data. So just to recap, last 3 weeks we have dealt with procedural abstraction, which really is really a means of organizing computational processes, okay, as a black box, right? So you specify inputs, specify outputs, and then you don't have to care about how the things are implemented inside, okay? So what it does again is that it abstracts away the irrelevant details, okay, and exposes only what you need to see, okay, which is actually the signature, the inputs and outputs, okay? And also it separates implementation from usage, right? So how you use the procedure is one thing, and how the guy who implements the procedure is a separate problem, right? All right, okay? And the last thing is that you can capture patterns, okay? And what you notice is that we use essentially procedures to actually aggregate smaller procedures into more complicated procedures, right? Okay? So this is the general idea. So last 3 weeks, we've been dealing with how to manage these kinds of operations, okay, patterns. So the key idea today is very simple. We can actually organize, okay, and reason about data in the same way, right? So data abstraction is really about the same thing, okay? And what you do is that you just need ways, okay, to essentially combine primitive data or simpler data types into more complicated data types, okay? So let's take a look. Okay, we will use the following example to illustrate what we want to do today. Okay, so you all know what rational numbers, right? Rational numbers essentially are numbers that can be expressed in what? In the form of ratio of two integers, right? So upstairs is called the numerator, downstairs is called the denominator, okay? And essentially, you obviously can use, you can apply elementary operators like addition, subtraction, all those stuff on these numbers, okay? So the thing about compound data is this. Typically, okay, compound data has two things. It has got a representation. Basically, you have to represent the data in some form, okay? And then it has also a bunch of operations that are applied on the data, right? Because fundamentally, data is useless, right? You need to be able to manipulate them, have them interact with each other. So The operations are normally, you can classify them into a few different categories. The first thing are called constructors, which are the procedures that's required or used to create the data. Okay. Then you have selectors, which allows you to, because compound data consists of what? It's a collection of small pieces of data, right? You must also be able to get at each piece individually, right? So these things are called selectors, which allows you to get at those pieces. Predicates allows you to ask questions about the data that's either true or false. Okay, and printers essentially lets you display data. Okay, so you definitely need to have these four kind of operations. Any questions? Question? If one is a question. Okay, so first thing, now we okay. You saw this earlier in the procedural abstraction. So now let's apply again. So for now, we just make a wish for the following. Suppose we have this thing called make rat. Okay, it's not make an animal. It's make rational number. Okay, so make rat returns you not a rat, but rational number. And you give this make rat procedure two things: the numerator and the denominator. Right? Simple. Okay, and assume somehow it returns you some rational number. Okay, you have no idea at this point how it's implemented, and you don't care. Okay, so this is the first part. And obviously, after you create this compound, this piece of thing called a rational number, you need to be able to extract out the numerator and denominator. That makes no sense, right? Okay, so you have two things: one called numer, one called denom. Okay, these two operations essentially will extract out for you the numerator and the denominator. Okay, simple. Okay, for now, the wishful thinking part is you don't care how it's done, just assume it's done for you. Okay. So, first of all, okay, you all know this, right? Who needs to revise? No need, right? Primary school, you learn all this thing, how to deal with fractions, right? So, you have two fractions, n1, n2, n1 d1 over, then the other one is n2 over d2, right? So, the way you add them is that you basically multiply the denominators, right? And then you do the multiplication and you add them together. Any questions? All know this, right? Anybody doesn't know this? Okay, so what do you do after this with this, right? With this relationship, right? What can you do? You can write this thing called add rat, right? X and Y. How do you do this? What is add rat? Make rat. Yeah lah, n1 So you essentially you don't use no brain required. You essentially look at this particular expression. Okay, you make rat of what? You extract numerator, extract denominator, you add together, and you divide again. Correct? It's really, again, no-brainer. So at this point in time, we are not doing anything smart, right? We take an expression. We basically just replicate expression in code. Are we all clear? Any questions? Okay? All clear. Very good. Obviously, you can add, you can subtract. Subtraction is like this. Questions? All clear, right? Very simple. Okay, so obviously, subtraction will be like what? How do you define subtraction? You add rat, what? You make rat. You take numerator, multiply by denominator, second guy, minus, the so forth. So this is the numerator of the first guy, multiplied by the denominator of the second guy. You minus what? The other thing, right? And then you divide the whole thing. So this thing will give you the numerator of the new rat. Okay? And the product of the denominators gives you the denominator of the new rational number. Okay? Are we all clear? Simple. Multiplication is like this. Okay? Are we clear? And obviously you know the division part, right? Okay, it's exactly the same as multiplication except you flip over the thing. Okay? Okay. Okay, so equality can also be done, right? Equality, you can check whether two fractions are the same. Okay, by comparing what? You cannot just compare the numerator and numerator, right? Because you know that they could possibly be different, right? And that the numbers can be the same. So you need to multiply the top and bottom and make sure that they're the same, right? Okay, so this is simple. Answer is what? You take the first guy, multiply by the bottom guy, then the bottom of the first guy multiplied by the top of the second guy, and you check whether they're equal. Okay? Now notice that I don't have to put the if here, right? I don't have to do if this thing is true, return true, otherwise return false, right? Because the operation itself will return you the correct value. Okay? And sometimes you need to flip the thing around, you just put a not in front. Okay? Okay? Alright. Now, so how do you display it? It's quite simple, right? You can actually write this thing called print red x, whereby you create a new line, you print out the numerator, print a slash, and print the denominator. Okay? So we have basically used the three basic operations, the make, red, numerator, denominator, and now we've fully defined all the operations, right, that we need to use. Okay, so, first of all, we are done with the sort of the operations that's required. We have assumed that these three things exist: make, red, numerator, denominator. Okay, and then we define all these operations. Okay, anybody unhappy? All okay, right? Makes sense, right? Very simple. So now we need to go back to the assumptions, which is the problem of wishful thinking, right? You pretend you exist. After you do all these things, you must then take care of the assumption. Okay, so now we take care of the assumption, which is to go and implement this. Okay, it turns out that obviously there is a way in Scheme to create objects. Okay, and the basic primitive used for building. Sorry about that. I got hooked. Okay, so the basic primitive used for building objects, complicated objects, is this thing called pairs. Okay, so the three things that need to know about pairs. Okay, the first thing is the command that's used to create the pair. It's called cons. Okay, so if you do cons xy, what it does is that it creates a pair xy. Okay, what is a pair? A pair is just two things stuck together. Okay, so that's really what it is. And then there's this thing called a car. Okay, which actually it returns the first part, the x. Okay, the first part of the cons pair. And there's a CUDA. Okay, CDR is pronounced CUDA, car and CUDA. Okay, why is it called CUDA? I have no idea, but this is how it's done. Alright, and it returns the second part of the pair. Simple? Okay, Now, examples, So suppose I define x to be cons 1, 2. Okay, that means essentially x becomes a pair 1 and 2. Okay, the first part, the car, is 1 and the CUDA is 2. Are we here? Are we here? Yeah? Okay. Now let's look at an example. Suppose you do the following. Define y to be cons 3, 4. Define z or z to be cons x, y. Then how? Then it turns out that the car of z will be 1, and the car of the CUDA of z will be 3. Okay? Are we clear? Okay, so the point is that you can recursively do this thing, and then it's fun. So the way to visualize this pairs is to do this thing called the box and pointer diagram. Okay, so essentially because these are pairs, right? So it consists of two things, right? Two boxes. Okay, and the way to look at this is to look at the cons as a pair of pointers. So they don't contain stuff, okay, but they contain some kind of like an arrow to point to stuff. Alright, so if you do the cons 1, 3 for x, what you see is the following. Basically, the cons creates this box, okay, and the left box, the first part of the box points to this value 1, and the second part of the box points to the value 3. Okay, and remember, what does define do? Define creates a mapping, right, in the environment table, which binds the symbol to a value. So the cons box is a sort of a value, right? So essentially, what happens is that in the environment table, the x symbol is bound to this box. Okay. Okay, So the left arrow, I say again, red one is the car, right arrow is the CUDA. Okay. Okay, then the thing to realize is that students like to do this, but the numbers are not inside the boxes. The numbers are outside the box. Okay, but the cons pair box only contains the two arrows, which are called pointers, which the C guys have a lot of fun with, but you don't have to deal with. For now, just remember, it's just like it points to stuff. Okay. All right. So next, suppose you define x to be cons 3, 7. Okay. Obviously, the diagram is on the right. Okay. This is how it's printed. It's printed as 3.7. Okay. It means if you type cons 3, 7, enter, you print out 3.7. 3.7. Okay. Similarly, if you do cons x5, y, what do you see? you would see something like this, right? Okay, essentially 3.7.5. Okay, and if you look at it, the diagram, if you visualize this, you see the following. Means the y points to the second box. Okay, second box is such that the first pointer points to this box, which is x, and then the second box points to 5. Okay, so the car of the y is 3. Why? Because the first thing you do is this. The car of y is what? Car of y is actually this thing, right? And then when you do the car of y, you're doing the car of y, which is 3. Okay. Obviously the car is a bit painful to write, so you can go car, okay, and then you get a little better. Okay. So that's kind of cool, right? All right. And similarly, you have CDAR, CADR, all those things, and essentially if you do CDARY, you have 7, right? Because you go down. Okay. Now, then there's also this thing called pair, okay, which is a predicate to check whether or not the thing is pointing to is actually a pair. What's a pair? A pair is actually the thing that is returned by the cons, right? This is called cons pair. So pair question mark, when applied to this thing, will return true. Okay? Now, it turns out that, okay, obviously your whole life will not be made out of pairs, because you need to do things that's more complicated than just pairs, right? So the reason why pairs is a basic structure is because once you can do 2, you can do 1 and 2, and you can string the whole chain up. Right. So the way that you kind of put more than 2 things together in schema or list is this thing known as a list structure. Okay. And the general idea is very simple. You chain up all these cons pairs in a train. Right. Now, obviously you can go as long as you want, and then you can have a whole string of stuff. Okay, so a structure of the following shape, which is cons until, and the last thing must be what you call a null. Okay, so remember this boxes, this cons pairs, is a pair of pointers, right? Okay, if pointer points to nowhere, it's called a null pointer. Okay, so if a structure that looks like this, like a train of cons pairs, and such that the last guy in the chain is a null, it's known as a list. Okay, and basically the list, this null thing is either represented as this thing or nil. Okay, nil used to work, but now it's called null. NULL. Okay, so it doesn't matter, you figure this out soon. Okay, so the general idea is this: you can it obviously again is a pain in the butt to keep doing cons, right? Okay, so again we are lazy. So basically there's a thing called list, which again is syntactically equivalent to cons. So instead of having this bunch of cons, you can just put list and then you put other pieces, and you will create the same data structure. Okay, it's very simple. This is just syntax. All right, and obviously, because the list is really a bunch of cons pairs, right? You can obviously use car and coulda on the list. Okay, and you can also use this predicate called null to check whether the list is null. If the list is null, if there's nothing there, then obviously the answer will be true. Okay, if the thing is not null, then you return false. Okay, are we okay? So far, this is actually nothing smart. We're just going through definitions. Any questions? Wuni? Okay. And who went for 8 o'clock lesson today? Wow. Very good. Still awake. All right. Okay, so let's take a look. Define x to be 1, 2, 3, 4. List. Okay. Car of x is what? 1. Very good. Coulda x. Okay, it's actually a list of 2, 3, and 4. Okay. Next. Cadr. CADR. 2. This. 3. Okay. So this thing is interesting. First of all, the quick thing is this. Obviously, you can keep going, but you can't keep going too far. You can have up to 4 pieces. So you can have a CAAAR. Okay, you can have CA whatever. You can have up to 4 pieces. Okay. Now let's take out clicker again and see whether you know what's going on. Okay, let's try this. Da-di-da. Hey, why is it you feedback? I don't know what to do. We done? Hey, hurry up. Hey, faster a bit lah. You're so slow. It's not presidential election, no. Nobody's going to get $4 million if you do wrong. It's okay. Hurry up, done. Okay. Oops. Okay. Where's it? Okay. So again, I've got two clues, guys. Okay, the 3 is correct. So essentially, you do coulda, and then car. So answer is 3. Okay. Can? All right. Good. Next one. Coulda, car. What's the answer? Hurry up. Dum-de-dum. Hey, y'all don't anyhow press, eh? What is this user feedback thing, huh? Can I tell you what, y'all anyhow press, I will go and deduct points, experience points, for people who mess around with me. Okay, so, the answer is what? Why? Because the car of X is what? 1, right? Then you coulda the one picks out and dies, right? Okay. Answer is error. Okay, next one. This one is what? Hurry up. That's not fun actually. Okay, ready? I think that's 37 of you, right? How many of you here? Somebody didn't bring sticker, right? It's okay. No experience point for you, sorry. Okay, next. What? You what? You always what? Really? Okay, we'll fix that. Maybe someone is not getting it because they got mapped wrongly to the wrong guy or something. Okay, anyway, the answer is what? It's faster. Okay. What's the answer? 5. Answer is 4. Because what happens is what? You do what? Okay, the first thing is you had this thing, right? You coulda one time you get 2. Coulda second time you get 3. You coulda one third time you have what? 4 in the list, right? And then you cut out the thing, you have 4, okay? This one? Dumb. So far not yet but okay there's no, okay, to be honest, no, there's no correct answer, wrong answer, but I think if y'all keep irritating me with the user feedback, I will deduct points. Because this whole thing is not to test you, you're right, wrong. This is to make sure that you're following, you're trying to do, so you're not completely bored, and then also to monitor attendance to know who actually came to lesson. How cool is that? Evil, right? Most brilliant thing ever done. Okay, hurry up, you're faster a bit, eh? Okay, ready? We go, Answer is, why 5? Why? Tell me, who is the guy who put 4? Why is that 5? What's the answer? Answer is now, Okay, this one. This one simple, Some you get wrong must deduct points. Okay? Answer is what? True or false? The question, this is the question. Is now what is now of X? Sorry, this question mark is the question. Sorry. So the question is, what is now of X? Is it true or false? Answer is obviously false. Very good. All very smart. Thank you very much. Yay. Is pair of X, again, very simple question. No brainer. Hurry up. Faster, faster. Okay, around there. Let's go. Okay, so hey, where's source? What's the answer? X is the list, right? So is it a pair? Yes, it's a pair. Okay, what is this? Dum be dum. That's a good question. Why is true or false? This one is typo, obviously. But answer is what? Answer is error anyway. Okay. So I typo here, sorry. This one? Hey, what happened here? Okay, so that is a typo also. The answer is what? Error. Okay, that's not true. But why is car error? Because the car is actually 1, right? Okay, and 1 is not a pair. So you try to car a pair, car a number, you have a problem, huh? Okay. So anyway, the answers are here. Okay. Now, so this basically gives you a quick overview on what we do with pairs, huh? Okay. Now we go on to the real stuff. Okay, so obviously we can try to implement the numerator using const, right? So one simple way of doing it is to make ret nd, const nd, right? Okay, whereby you just put the numerator and the denominator together into a pair. Okay, and then essentially you can just define the numer and denominator to be the car and the CUDA. Very simple. Okay. Now, so suppose you do that, what happens? If you define 1/2 to be make ret 1, 2, you have obviously half, right? Questions? No, right? Very simple. Now 1/3 will be 1/3 lah. Eh? How come? Because you add, right? So 1/3 plus 2/3 is 5, 6, right? Okay, very good. Next. Suppose I multiply 1/2 by 1/3, I get what? Okay, very good. Suppose I do 1/3 plus 1/3, I get. Oh, how come? Yeah, because the point now is that in the definitions, I just did some stuff of it, add and divide. I didn't reduce to lower terms, right? Okay, so obviously it looks kind of nasty. For now, it looks okay because it's small. When you do bigger numbers, it looks really nasty, right? So you don't want this. Okay, so how do you fix this? Okay, so the first thing we can do is that we can reduce lower terms, okay, by modifying make ret, right? Which means that make ret nd, okay, how do you do GCD? Euclid's algorithm, right? We did a few weeks ago. So essentially what you can do is that in make ret, you can do a let G be the GCD of n and d. And then instead of actually storing n and d, we store what? You store the n and d reduced to lowest terms, right? So basically when you do this, obviously your answer will all end up in lowest terms. Okay? Okay, so now we do print ret of add ret 1/3, 2/3, you get 2/3. So like 1/3, 1/3, you get 2/3. Okay? So now is the idea of abstraction barriers. Okay? Now, I think some of you got points taken off for the procedural abstraction, because you basically are doing some stuff that by peeking into procedure. Similarly, the general idea of data abstraction is this. Okay, in data abstraction, what you can see is that you can go and basically organize all your procedures and the data types into different levels. Okay, and at the bottom, obviously, are the implementation of the pairs, which you don't have to care. Okay. What you know, however, is that scheme gives you const, car, and CUDA, and you can use these 3 primitive procedures actually to create your pairs, and those are your primitive data types. Right? How they're done, you don't have to care. Now, after that, what we did is that we used this const, cars, and CUDAs to implement make ret, right? Okay, and basically we use pairs to represent rational numbers. Now, above that, we have this addition, add, subtraction, and things like that, okay? Whereby they only use what? Make red and number and denom to actually do the stuff. Correct? Okay? Now, not that the following is true. Note that you don't, okay, if you know, for example, that your rational number is a cons pair, right? You don't actually need make red, right? You could actually have done all your operations in cons. Correct? Yeah, but that would be what you call breaking the abstraction. Essentially, you want there to be a layer of stuff here so that you don't directly access the primitive representation. Now, why is that so? Protect what? Protect what? Who's in danger? The user. Okay, so the example is this, right? Just now what we did was the following. We went to do what? We went to actually do the reduction, okay, in terms of the lowest terms where? In make red, correct? Remember? Now, it turns out that I didn't have to do that, no? I could have just stored ND as it was. But instead, in the numerator and denominator, I could have done this reduction, right? Correct? Are they equivalent? Yes and no, right? They are equivalent where? They're equivalent, okay, from perspective of you operating above make red and numerator and denom, they are equivalent, correct? But below they are not equivalent, no? Right, because the way you store the data is actually different. Okay? So the thing here is that you are protecting somebody. You basically, the point now is that if you break abstractions, what happens is that when changes happen, basically somebody gets blown up. Right? Whereas if you actually maintain these abstractions and do not break the barrier, it means you actually follow those contracts. Okay? You basically will be able to make changes in a kind of transparent way without blowing things up. So here, my point is that I can improve the make red and numer and denom in different ways without having to kind of cause damage to you when you're using this operation. Now, in fact, I can do a third way, right? A third way is actually to reduce when displaying. It means I actually store the thing the way that I want to store, and I only go and do reduction when I display to you. Okay, so there are many ways of achieving the same end. Okay, that is invisible to the user. Okay, so the point now is that, so see, what's the problem here? The problem here is that, so what am I saying here is this. Suppose you create this thing called make red. Okay, you create this red using make red, right? You know that make red gives you a cons pair. You can suka go and use car encoder to extract things out, right? You know what I'm saying? But that would be breaking abstraction barrier. You're supposed to use numer and denom. But if you use cast encoder, can you extract things out? You can, no. Right, but then the problem here is that you don't know what I'm marking around here, what am I doing? So if you don't know what exactly I'm doing underneath and you just extract stuff randomly, and I went to change the representation in some way, then your program is all messed up. Okay. However, if you basically comply with my abstraction, then I can go and improve the implementation, change it, and it shouldn't affect what you do. Okay, so this is the idea of not breaking abstractions. Okay, so this thing is known as contract, okay? Because the whole point here is that I tell you what you're supposed to do, okay? And you don't have to care how I do it, okay? As long as I do the right thing, okay? So this thing is known as a contract. So this abstraction barrier idea, okay, allows us to basically choose different representations, and even more significantly, to on the fly change the implementation without telling you, and you should not have any problems. Okay, so this is the general idea. Okay, so the thing is this. Now that we have talked about this idea, let's just do an example, okay? And the example is, okay, cons and car encoder all done for you. But this class is very annoying, right? We keep doing the obvious, right? We're implementing stuff that you know already given. So let's try to implement cons and car encoder. Okay, suppose I feel like it, I can do this, right? I can implement cons as a what? As lambda, right? Okay, and how I will do this the following. I will say cons xy to be lambda m, okay? And inside m, I have three conditions. If m is 1, I give x. If m is if m is 0, I give x. If m is 1, I give y. And otherwise, I freak out and I die. Because it's not supposed to be anything else, right? So, okay. And then, how do I define car? I say again, suppose this is actually the definition of cons, right? It means I say con xy would be this. How do I define car? I couldn't. Okay, so car is what? Define car z, right? Car z, which is what? I say again, define car z is z0, okay? CUDA will be z1. Are we clear now? Because when you do cons, what happens? It returns you actually a lambda object, right? And what you really need to do in car and CUDA is to unwrap the lambda and return the stuff that's inside. Okay? And what happens here is that the lambda is lookup table, where you put in 0, you come out one thing, look up, put in 1, come out the other thing. So this is the way you implement it. Okay? And then suppose you do this, and then it works out, obviously. Now, it turns out that I feel like it, I can do this also. Okay, sorry, this is kind of obscure. But I can define cons xy to be lambda m xy, cannot? Cannot? Anything also cannot? Obviously can. So, the question now is, so given if I change to this form, if I define cons xy to be lambda m xy, what is car now? How do I define car z? Lambda xy? Lambda xy return x. Okay, so car z would be, okay, z lambda x lambda pq return p. Okay. So you look at this, you see obviously clear what it is. Others look at you, you like, what the heck is this? Life like that, okay. So, okay, stare at this some more. So, what is CUDA of z? PQ return Q. Okay. How many of you are still confused? Okay, stare harder. Okay, never mind. I tell you what. You all keep staring. Between now and this afternoon, what happened to you, ladies? Come, here. You have front row seat reserved for you. You brought a friend some more. Come for next class. But I'm very handsome, so you can't see me also, right? Come, sit down. Okay, come here. It's okay. It's okay. Yeah. Alright. Okay, so obviously this wing works, right? Okay? Can? Alright. Now, so we'll talk about this again this afternoon, recitation. So between now and 2 hours from now, you can keep looking at this some more and see you can unconfuse yourself. Okay, but this works, okay? Now, okay, so it turns out that these two ways are just for fun. Okay? We are not going to be able to ask you to implement this thing. I'm just using this example as a means to illustrate to you what is a contract, right? A contract means what? It means that I tell you this is how it's done. Okay? Give the inputs, this are outputs. Okay? And the implementation must follow the contract. Otherwise all things break. Okay? Scheme will do this better, obviously. Okay? But the point here is that any implementation is okay as long as you basically fulfill the contract. Okay? Now, because of abstraction, actually, this is the key idea, right? You don't have to care how cons, car, and CUDA are actually implemented. Okay, so now we will go to the next part. But before we go to the next part, let me just highlight some important idea. First of all, how many of you are taking 1, 2, 3, 1? All taking, right? 1, 2, 3, 1. Except for the NS high. Okay, so you know this, right? Humans make mistakes. Okay, you are only human, therefore you make mistakes. Okay, so the last part of this class we'll talk about debugging. Okay, but then before that we'll go off for a short break. Okay, and I will show you this little video which I had a hard time trying to get to work, but okay, it is called 5-Minute University. Okay, 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 I guess I'll let him do the talking. Okay, those of you who need to go to the bathroom, you can carry on.
Education, I think it don't matter where you go to school. Italy, America, Brazil, it's all the same. It's all just memorization. And it don't matter how long you can remember anything. just so you can parrot it back for the test. And I got this idea for a school I would like to start, something called the 5-minute university. And the idea is that in 5 minutes, you learn what the average college graduate remembers 5 years after he or she's out of school. With the cost of like $20. That might seem like a lot of money, $20 just for 5 minutes. But that's for like a tuition, cap and a gown, the rental, graduation, a picture, snacks, everything included. You know, like in college, you have to take foreign language. Well, at the 5-minute university, you can have your choice. Any language you want, you can take it. Say if you want to take Spanish, what I teach you is, ¿Cómo está usted? That means, how are you? And the answer is, muy bien, means very well. And believe me, if you took 2 years of college Spanish, 5 years after you're out of school, ¿Cómo está usted? Muy bien, about all you're going to remember. So in my school, that's all you learn. You see, you don't have to waste your time with the conjugations, vocabulary, all that junk. You just forget it anyway. Now, what's the difference? Economics, supply, and demand. That's it. Business is you buy something and you sell it for more. Theology, I'm going to have a theology department, you know, since I'm a priest, it's all right. And what you have to learn in theology is the answer to the question, where is God? And the answer is, God is everywhere. Why? Because he likes you. That's kind of a combination of the Disney and Roman Catholic philosophy. It's just perfect for the late 70s or early 80s, you know? Just perfect. Well, after the courses are all over, then it's time for a little Easter vacation. No time to go to Fort Lauderdale. Only lasts like 20 seconds. But what I do for you, I like to turn on a sun lamp. You know, I give you a little glass of orange juice. That's the snack part, orange juice. And then after vacation, you know, after you swallow it real quick, then it's the time for the final exams. I say to you, ¿Cómo está usted? You say, muy bien. Where is the God? The God is everywhere. Economics, supply and demand. Then I put on your cap and a gown. I get out to my Polaroid, the camera, you know, make a little snap and flash a picture for you. I give you the picture. You give me $20. I give you a diploma, and you're a college graduate, ready to go. And I'm not sure, but I'm pretty sure, right next door to the 5-minute university, I might have opened up a little law school. You know, you got another minute?
All right, very good. So, whoa. Okay, you can go in your spare time, right? For now, we will come back to this. All right. So very good. How many of you think you're writing scheme code in 5 years? Well, not 5 years, 9 years, right? Because you need to graduate first. How many of you think you're writing scheme code in 9 years? Nobody. Very good. So, if you forget everything, and people ask you, what the heck do you learn? 11S, tell them, manage complexity. Excellent. Okay, very good. Okay, this guy is wondering. Okay, so, manage complexity. That's all you need to know about scheme, right? And the truth is this, scheme is quite useless in general, but it turns out there is one firm which is called Jane Street, on Wall Street, which actually uses OCaml. And OCaml is some functional thing. So they can't find people teaching OCaml in school, so they make do with scheme programmers. Okay, so this is and if you do like your Google, or Gmail, right, and then you have scheme inside. Sometimes you see your ad on the right side. Okay, all right. So this is something you learn probably in 1231, right? So it's like you are human. Humans make mistakes. Therefore, you make mistakes. Okay, so, and also, who was bitching about this? David, right? Alright, so essentially, the problem here is that, this is the truth, right? You will be writing code, obviously, and it turns out that, alright, more of your time typically is spent doing this wonderful thing called debugging than actually writing the code. So, I have a very simple solution for you. Don't make mistakes in your code. Then no time, no problem with this. So, but in case you do make mistakes in your code, then you have to go through this fun activity called debugging. And let me tell you the secret to life. In your practical exam, if you don't make any mistakes, you can finish in 10 minutes. You type, enter, you can go home already. Seriously, I mean, the amount of code you type out in practical exam is about 10 minutes worth maximum. Okay, if you have fast fingers, 5 minutes will do. Alright, so debugging really means to remove bugs from programs, not spray baygon. Okay, and the thing about debugging is this: debugging, sadly, is activity for which you don't really know whether you are completely right. Okay, you just pray that the prof doesn't find stuff that you didn't find. Okay, pretty much that's it. Right. So, and then for huge programs, obviously you just hope for the best. If you are Microsoft, you have no hope. But other than that, you try your best. Okay. So the whole point is that you try your best. There actually are techniques which are called model checking, formal verification, that can completely, prove that the program is bug free. But right now, those techniques typically can only be applied on smaller type programs. Okay, which is why you still have bugs in large programs. Okay. So the first obvious thing that you have is this problem of incompatible types. Basically, you can define x to be 5, and then you can define square x to be this times this, okay? And then you do like plus square x or something. So here, what happens? X is what? X is 5, right? Square is a procedure. So here you're trying to basically add a number to procedure. Obviously, you fix it and dice, okay? Or you're trying to do 3 square. Instead of square 3, what happens? 3 will be a what? A number. You try to apply a number onto a procedure, again, it's fixed and dice. Right. So these things are actually type problems. Okay, so this problem is a problem for Scheme, but not for Java. Why? Because those programs, those languages basically are type checked. Okay? So that means you will actually see the compiler will actually tell you that it's a problem. Okay? But the fun thing about Scheme is that it lets you do everything you want. Okay? So this one freaks out and dies at runtime. Okay. So essentially you must be careful with different parts, okay, of your expression, what kind of types they are, and make sure you do the right things. Another thing is number of arguments, right? Okay. So oftentimes, one thing you must learn is this: when you basically do the Docker scheme, right? You have this error messages. Okay. You have to learn how to interpret what they mean. Okay. So for example, in this case, one example here, they will tell you like arguments. I forget what exactly the error will be, but the down scheme, something like that. So you look at those error messages, you will hopefully be able to tell what the heck's going on. Okay. And another problem is this: this incorrect arguments. It's very common. When the argument is not a simple thing. It's some ginormous piece of thing that has many brackets. Okay. At some point, you know, by the time you reach the end, there are like 5 brackets and then a number, and then another 5 brackets. Then like, what the heck, is it 3 brackets and 1 number, or 2 brackets and 1 number, or 5 brackets and 1 number? I mean, you kind of. So those the bracketing problem basically can cause this argument problem, right? How do you avoid this? In basically, and new line, next line, you go and match up the thing, Okay. So there are some techniques. Basically, if you format your code properly, you should be able to avoid some of these problems. Okay. Syntax. Obviously, you end up doing 3 plus 5. Life's not good, right? Okay. So, who was compared to syntax? David again, is it? What did you? Correct. So somebody compared of syntax. So Scheme probably has the simplest syntax ever already, right? Because it's always operator in front, apply eval, right? So it's really quite simple. Okay. So the reason, if you have trouble with syntax, let me tell you why. It's because you're doing this thing called anyhow whacking. Okay. Because if you're thinking hard about what the heck's going on, the syntax should be quite clear. right? The set truth is that with the if you are coding on Docker scheme, right, some students will just basically anyhow whack. They try enter or plug, and then they'll remove one bracket, add one bracket, roll. It works. Okay, good for them. And then continue. Right? Okay, so the problem now is that if you do this technique of debugging called anyhow whacking, then it might work for this class because we're doing simple things. Okay, and sadly it might work. All right, but I would recommend that you think a bit harder about what you do. Okay. Next, obviously, you can have this error. What is this error about? This is the divide zero error. But obviously, this is actually quite easy because you can actually they'll freak out and die and tell you this. So it's not very hard to figure this out. Okay, the problem here is this. Here is obvious because y is actually shown to you as 0, right? So the problem here, this style of error is a problem when you have variables that change over time. And when you look at the code, it's not obvious that it's going to be 0. Okay, this is when life gets a little dicey. Okay? Next, obviously this one also tells you, okay, again, scheme will freak out and die and tell you this thing is undefined variable. Basically, you can have this type of thing happen. And these things can happen actually in some kind of conditional statements, right? Basically, if something, something, something. Note that if something, something, if mostly is always true, you always run the first part. And the second part may not be run, okay? But after a while, for some other conditions, you may run the second part and the thing will freak out. Okay, so be careful when you have like if statements, conditionals, because there are some branches that are not being executed all the time. You may not be able to see them with the errors there. Until it happens, then you see. Okay, this one is very common as well. What's the problem here? Okay, so this code looks right. I mean, it looks kind of right. I mean, because it actually does look right. If the factorial, if n is 0, you return 1. If not, you return the star n factorial n minus 1, right? So the code looks right. But then what happens is you enter like factorial 2.1, then, well, you wait very long. Right? Because the problem here is that your terminating condition, right, basically is not strict enough, okay, to catch the termination, right? Okay? And so similarly, you can have things like this. You also, if the inputs are kind of unexpected, negative or something, and you keep counting, things can get hang. Okay? Another thing to understand is this. Your code may be correct, but the problem here is that you must understand also that, okay, scheme is interesting because scheme will have this property known as infinite precision, right? For integers, for rational numbers. Okay? But if you divide by 0.01, 0.1, once you hit the point, something come in, right? Essentially, you're forcing scheme to operate in the floating point. Okay? Once you operate in floating point mode, right? Then the floating point essentially means that you give a finite amount of memory to represent the number. Alright? And if the number is too big it's not the number is too big. If the precision number is too high, and essentially it's beyond the precision of the amount of space that you have required, right? Then you lop off some small small parts for you get some errors. Okay, and then when you do multiplication, division, the errors will actually get bigger and bigger. So when you work with floating point numbers, and then you try to basically test for equality, it is possible sometimes that this case may not blow up, but it is possible that they may never, you may have some minor errors over time, and this can cause you to have problems. Okay, so obviously another thing that can have problems will be logic. So what's wrong with this? This one, basically the syntax, everything is okay. You run fine, right? Answer is wrong, right? Because there's typo, right? Obviously. Okay, so in this case, the typo will never shows up actually anywhere as errors, right? Because it's not really an error. Because you never know that you may want to compute this thing, right? So this is the logical errors which basically comes from your code. So how to debug? Okay, I mean this one there's no real like technique to debug lah. You just have to do more and then figure it out. So there's some simple ideas lah. So you must think like detectives, and basically you must be systematic about this, right? You cannot do anyhow whacking. Okay, sadly you can anyhow whack for this class possibly because the programs are small. Okay, but if you are more systematic, hopefully you'll be faster. Okay, and you don't have a lot of time for practical exam. Okay, So look at the clues. First of all, now, let me just say this once and say this good. You guys now have this, okay, now we upgraded the GFDI Academy, the system there, you put in your code, it does indentation for you, it does outlining, right? That one, okay, do not, some of you are doing it, but please make sure that you run your code actually in Docker Scheme, make sure it knows no bugs, cut and paste into GFDI Academy. Okay, don't just type your code out and hope that it works. Okay? I'm serious, people are doing it, some of you. And the thing is this, you also must try your best, try to do more work with this Docker Scheme, because you want to learn what the error messages mean. Right, because the whole point is, one of the key things about debugging is that you must be able to see the error messages and quickly fix. Okay? Next. Eliminate impossible things. Okay, we know it's not going to be a problem there, then just ignore that. And then you basically also want to perhaps run the program with different inputs. Okay, to test. Okay. Then the question now is, does the error occur again if you use the different input? Okay. Work backwards. Okay. And then essentially, okay, one thing obviously is that you can we use visual thinking. That means you can take a big problem, solve it instead of smaller problems. And what you may want to do is to go and check the small pieces first, make sure they're really correct, and then move upwards. Right? Because if you're sure that this is small piece, like the sum of squares is correct, then it's correct lah. Right, then you know that error is not there, you move upwards, okay? And then, okay, Docker Scheme as a debugger. You all know how to use this now? Who here knows Docker Scheme as a debugger? Who doesn't know Docker Scheme as a debugger? What's a debugger? Sounds like a vulgar word, but it's not. So the debugger is this thing whereby you can debug and then you can step through step by step, right? You can set breakpoints. You ever done it before? I think they're breakpoints, right? No? Step through. Okay, but okay, so truthfully, okay, you know, obviously from what I say, I don't do debugging in Docker Scheme very much. And clearly I don't need to use debugger. Okay? But most IDEs have this debugger facilities. You can set breakpoints, you can do step by step through. Okay? And then another thing you can do is what you call trace procedure. Okay? And tracing procedure means you print stuff. Okay? And one simple thing you can do is display variable names. Okay? Values, sorry. Okay, so let's take a look at a simple way of doing it. This is a bit low tech. Okay? I used to do this when I was young. Obviously, you can probably do better using some debuggers. But a simple way is this. You can define this thing called debug printing. Okay? And you can set the false. Okay? Or you can set the true. The question here is, do you want to print? Do you not want to print? Okay? And then you can create this thing called debug print XYZ. Okay? No real reason. Just do this. And then the first thing you do is check whether debug printing is true or false. If it's false, obviously do nothing. Right? If it's true, then you do the stuff, begin this thing. And what you do is you just write 3 lines, X, Y, and Z. Okay, suppose you do have this helper thing. Now, suppose you have foo. What does foo do, quickly? It tries to add a number from point 1 of a number until from 0 until n, right? Okay. So what I've done here is this. I've added this thing called debug print counter n result. Okay, which means that when you go okay, so essentially what happens is that foo is iterating, right? Remember? Now remember iterative procedures, right? You have this. I always do for you the example, right? Whereby iter 1, 2, 3, right? Then next line, so forth, right? Okay, now if you are able to print out the whole evolution of the computation, obviously you can see what went wrong. So what I've done here is that I've actually inserted a line called debug print, whereby I'm printing out the counter, the end result. Okay, and the reason why I have this debug printing here thing is because after I'm done debugging, I'm too lazy to remove the line. Okay, but it's damn annoying to have this thing printing all the things all the time. So if you do this kind of global flag, you can turn off the debugging, and then you will be able to run the program without being annoyed. Okay, so this is a simple idea. Okay, now another thing you can obviously do is following. So you flip n, right? This is the bug, right? Remember? Okay, so you can do a if in the beginning, begin debug print, and then the less than 2. Remember that what? Begin returns you, what's the return value of begin? It's the last thing, right? So what debug print does is actually does nothing if you turn off debugging, the printing, right? Okay, so these are things that you can do to insert some print statements into the thing. Now, another thing is this. Another thing is that you may also want to insert your assumptions clearly into the code as kind of like your comments, so that if other people are using your code or or God forbid use your own code, right? You don't forget that what assumptions are made in the code. Right, obviously you can take care of all these issues if you want to, but you didn't take care of it, you must make sure that you highlight the assumptions clearly. Okay, and another thing is this, okay, now, for the practical exam, right, you are likely to obviously solve problems that are not so simple, right, not completely trivial, right, and essentially the solution is likely to consist of several procedures, some smaller ones and some bigger ones. Hey, for goodness sake, don't write everything and then you debug and then boom, explodes. Right, so the point here is that you probably want to test each procedure, the small parts one at a time before you could continue, okay? Because that makes your life better and improves sanity, okay? And you also want to check your boundary cases because oftentimes things blow up. Now, for example, one example would be remember the recitation example where we do the countdown? What's that? What example was that? There's one example where we counted up and counted down. Which one is it? Not new problem. This one whereby the second we did a count up and count down. The iterative version, right, of flip or something. Okay, so you can count up or count down, right? Now, so the thing to note is that you count down, you will match what? You match to 0, right? Count up, you will be bigger than n, right? Okay, so it's not equal to n, it's bigger than n. So these are little things that you must make sure you get correct. Okay, because these are the smaller boundary conditions where we test whether it's bigger than, equal to, or whatever. These are where mistakes happen. Okay, so now what we'll do is that we'll go into live demo. Okay, so for all live demos, I'm going to saw somebody. I need to have a volunteer. Do I have a volunteer? You. Okay, one volunteer. Anybody else has a volunteer? So who are all the volunteers? Come. Very good, very good. Okay, okay. We take this Chancy. This guy is very idle one. You lah, yeah. This guy is very idle. So better give some work to do. I'm idle. Okay. Let me tell you what fun thing he's going to do. Okay, the fun thing. How are we going to do this? Okay. Now this demo is very interesting. Okay. What we're going to do is very simple. Okay, you go IVLE. No, you don't log in. I log in already. Okay, so this is IVLE. Okay, obviously this is my account. Obviously, now then you look inside here. Okay, there is this thing. This is the work bin, right? Okay, now there is a directory called exam. Inside there are 45 documents of all sorts. Okay. So what we do for demo is very simple. We will look at practical exam 08. Okay. And Mr. Shenzi here will on the fly do question 1. Woohoo! Now, okay. Obviously, he'll be so good. He tests out, there's no errors. Then how? Demo fail. We find another victim. Okay? But in case there are errors, okay, we will here have a live demo to see live debugging. And the question goes as follows, okay? Okay, this is supposedly your warm-up question. So essentially, you are supposed to write this procedure called contains. You give him 2 numbers, okay? There's a first number, and there's a substring. Right, so for example, if you do 1, 2, 3, substring 1, 2, the answer is true, because 1, 2, 3 contains 12. Right? The next thing you have is 1, 2, 3, 1. The answer is true because 1, 2, 3 contains 1. You do 1, 2, 3, 4, 5, 6, 7, 8, 99. The answer is false because 1 to 8 does not contain 99. Okay? And very good. And so now we shall have Dr. Skin and Mr. Shenzi would hereby demo for us. Where's Dr. Skin? That was the practical exam. Where's Dr. Skin? Racket. Okay, come. Ta-da! Here you go. You have long enough. Yo, come, let's go. Okay, this time the Chinese say, 掌声鼓励鼓励. No, just write on the fly. Okay, now you want to talk through your code or just want to write? Just write. Okay, so I say again, the problem is very simple. No, wait, the problem not very simple. It's okay simple. No. You remember now? It's just write what the procedure contains. You have got A and no. What are you doing? It's here. It's here. Hey, what are you doing? This is the problem. This is your scheme window. Okay. Carry on. No. Okay. Another thing about this whole demonstration is this. Please do your work in the upper window. Cannot. You all know, right? Okay. Who here haven't figured this out? Okay, you haven't figured this out. Then let's get it straight. So you should really do your work in the upper window, right? Bottom window can work or not? Can work, but then it's very painful, right? Okay. Then you type your code in the upper window and you press run. Okay. You all know this, right? Okay. Define, I tell you what to do, contains, okay? No, not contains, and contains. Right, which one first? Okay, so just watch. Hey, just watch. Will you watch live demo? Okay, so now I'm like a sports commentator, right? So what he's doing now is that he's writing length. Okay. Okay, actually, how would you probably do this? I would suggest actually what you do is that you can start off with, first of all, define contains X and Y, right? Because Y, that is actually the signature for the entire solution. And then you can consider using like what do you call it? What's he doing? Oh, he's defining the length of X. Okay. It's not modulo, remainder, right? Does it modulo work? It works. I'll tell you quotient, sorry. Quotient, sorry. Here I'm confusing him. He's under a lot of pressure. Sounds right, Okay, so notice also that he's actually using the Docker scheme, right, to check the the parentheses, okay? Do you have what? Exponentiation. I think it's EXPT. Yes. Those of you who have laptops are very free. I can challenge him and see if he can do faster than him. Yeah, of course. But life's not fair, right? It's okay. Can test the code, run . No, okay. So first of all, he's doing live demo, which means that you're not supposed to type in the perfect code. In fact, you better make mistakes, otherwise my demo will fail. So okay, press run, right? You can press run, whatever, to run the code.
I can run it multiple times.
Yeah, of course. No, you just press, okay, you know how this works. Part of the problem is to make sure that you understand how to use Docker record. You run, you can see the problem already.
Wait.
Hey, I tell you what, sir, I give you a seat. Come. Good service, right? Hey, don't laugh at him, no. You all better think through and ask yourself whether it's working or not working, what's going on. Okay, first of all, obviously it tells you bad syntax. What's the problem here? don't be sorry, it's okay. Thank you. I thank you for a good demo. Actually, in fact, so your definition is wrong. So it contains, not contains n. So actually, okay, the thing is this, another trick to understand is this, you don't have to put it here. I would recommend you do it up here instead. Cut and paste. No, as in this thing, you probably want to control C, control V. Okay? So, yeah, so every time you just keep running, right? So that it's okay, it's broken, but then here, at least you just keep typing the thing. Okay, so part of the point of this demo is to illustrate to you how to do these things efficiently. Typically, actually, I never use the bottom window ever at all, because it's quite annoying, right? Everything you do will be erased. So you do all your stuff on top, okay? And then you just keep running. Okay, so the answer is what? 3, right? Okay, it's already off the screen, but the answer is 3. So he knows that his length 1, 2, 3. It seems that it's working right. Okay, so one thing he's doing now is that he's actually testing his what? His helper procedure to make sure that it's sort of working. EXPT 10 to the length of this thing, he runs and sees 10,000, so he looks happy. No, he doesn't look happy. Why aren't you happy? He looks like, right? Wow, he's getting help from the ground, he's getting help from the crowd. No. Okay. How? Okay, Richard, go, help him. So this is what is known as a logical bug, right? Okay, so let's quickly, while he's struggling here, let's talk through the solution. What is going on? So you have two things, right? You have a x, which is the long string. There is a y, which is the substring. Okay, what is the logical way of doing it? Basically, the simple thing to do is to do recursion, right? No, don't. Yeah, you can obviously convert the string and then do string some regular expression check. But a simple way of doing it is the following, right? You have two pieces. You've got the left piece and right piece. You take the last few digits. You check whether they are equal to the left to the y, and then if they're not equal, if they're equal, you're right. If you're not equal, what do? You chop off one digit and you shift it down, and you keep doing recursion on the. So you're recursing on what? On x, right? The x and y, right? What you want to do is you want to basically recurse on x by chopping off one digit at a time and matching the last few digits, right? So that's the idea. The idea here is that you want to check whether y is equivalent to the last few digits of x. If it's not, basically you chop off the one digit and you keep trying. Okay, you do it until what? Until the x is smaller than y and you're done. The answer will be false, right? So he has done exactly the same that, but then he checked, he did if, he realized, you need more than that. So now he's going to a con. Okay. Alright. Okay. Alice. You want to do what? Lop off one digit, right? Okay, so is this correct or not? Okay, so wait, hold on a sec. So what you want to do is this. Okay, so what you do is that you have written out the answer. Okay, what should you do next? you should create a few test cases, right? Okay, so it contains some things, okay, and then you try and you see, whoops. So answer is this correct right now? So obviously your answer should be, okay, 3 and 4 is true, but then 3, 4, 5 does it contain 4? So the question here is, contains n, is it correct or not? Okay, so what's the problem here? Test is wrong lah. Contains, right? No, it's question mark. This is true. True. How? Seems to work or not? Just two, right? Next time I guess ask volunteer, nobody will do it already. You comment out all the. Okay. All right, thank you very much. Okay, so very good. So this first example, what you've seen him do is that he has basically got along the way, right? He doesn't get it right the first time. Okay, so essentially you need to go through first of all, the key thing here to realize is that you must first of all figure out what the heck you're trying to do. Okay, how come up with a strategy to actually solve the problem, right? And then after that, essentially you will go and write the thing, obviously. Okay, and what he's done is that he has written some code. And one thing is that as you go along, right, it's helpful to have some test cases. Okay, so the thing is that for the practical exam, essentially I'll give you some test cases of it. Okay, obviously there will be test cases that I don't give you, right? But minimally, what will be helpful is that if you have test cases here, right, and then you write a code on top, you press run, you should be able to see all the test cases and you can compare and see the right. Okay, yes, Salah. What happens? I think I said no zeros or something. Okay, so this is the problem, right? So here, basically, you have wait. What's the problem here? This is the boundary case problem. Okay, excellent point. So these are kind of essentially boundary case problems whereby you need to check for all these kind of weird boundary cases. Okay. All right. So a few things to note. So this is a little bit natural. So typically, one thing you want to do often is that instead of using define, right, it's more natural to use let. Okay. Okay. So this is okay. So typically, it's not very natural to use define when define, right? Okay, define would work, but normally style-wise, let is a more kind of more I don't know, natural way of doing it. Okay. Any other questions or comments? Okay, you all understand how this works, right? In terms of the flow. Okay, essentially what he's doing is he's checking whether the lengths are the same. If one is shorter than the other one is smaller than the other one, is obviously false. Okay, and then he's checking the last few digits to see whether it's the same as the y. Okay, if it's not true, then if it's true, then it will be true lah. You find the substring, right? Otherwise you can't. Okay, why does this thing return true? So the problem now is that this thing, and okay, y is obviously what? Y is 0. And then x, okay, then y is 0. So y is 0 here, length 0. Length is 1, 10. Okay. So how? So essentially, say again? Okay lah. Anyway, you're gonna think about this thing. Okay, think about how to fix this. Okay, but the point now is that be careful about this. This is a very interesting example, whereby the boundary case actually causes problems. Okay. Yes. So you have to think of how to do this properly, all right? You basically need to fix the algorithm a little bit to get this right. Okay. Now, so this is done. Okay. Let me quickly finish it. Okay. So summary. Okay. So I'm pretty much done for today. Okay, so the first thing we talk about today is the use of cons, okay, to glue stuff together, to produce bigger pieces of data. Okay, and you will see this very soon in the next missions, okay, when you use RSA, when you use cons to build RSA-like things, okay. So the abstraction barriers essentially allow us to separate usage of compound data from its implementation. Okay, and moving forward, right, you'll be obviously using cons, okay, to basically implement data types. Okay, now if you guys in your code end up using car and CUDA to access the insight of data types, okay, you will be penalized in your homework for breaking abstraction barrier. Okay, so only the procedures at interface we use. So essentially, if you define a new data type, okay, you need to make sure you define the constructor which creates the data type. You must also define all the operations necessary to select the different parts of the data type, and also to basically modify the data type. Okay, you should not be modifying the data type directly in terms of cons. Okay. No, but then the problem now is that you can't, because you will have to say that I define new data type. It may be a curve, right? Okay, the curve is lambda or whatever, but the curve could also conceivably be defined as a pair. Okay, now if you know, even if you know the curve is defined as a pair, you shouldn't be actually going inside there to modify the curve using the cons and cars and CUDA. Yeah, correct. You need to use x off and y off, correct. So the point now is that, let's say the curve thing, right? You know for a fact that, let's say you know, look at the code, you know that the curve the x and y is a cons pair. You should use x off and y off instead of using the car encoder. Because if you use car encoder instead of x off and y off, you are actually breaking abstraction. Okay? So the whole point is that the key idea here is that once it's a contract you define, once the contract is fulfilled, you don't care how it's actually implemented. Alright? And these are three primitives. Okay? Debugging, basically we've gone through it's not obvious. Debugging is really a kind of an art. And there's no real fixed way of doing it. You just have to do it more often. Okay? And the interesting thing to note about debugging is this, right? As you get better and better, does it get easier or harder? Why? You get better, right? Because the strange thing about programmers is that it's very irritating. The higher skill level you get, the worse it gets, because all the easy bugs you don't make anymore, right? You make this obscure, nasty bugs, okay, which is very high level bugs. So good and bad, okay? This is the homework for today, okay? So the idea is this. The idea is that in life, we need to implement this thing known as abstract data types, okay? And you need to implement abstract data types and also basically procedures associated with it. So today for homework, go implement this thing called a set, okay? A set is obviously, you all do 1, 2, 3, 1, right? You all have you gone through set already? Soon to be, soon to go through set. So you create this thing called a set, right? And obviously you can add objects to the set. Obviously you can remove objects from the set. And obviously you can check whether a set contains an object. Okay? So basically based on today's lesson on cars, cons, and CUDA, you are supposed to be able to basically write these 4 procedures which will allow you to essentially define, create, as well as manipulate this data object, this abstract data type called a set. Okay? Sorry? You can write with lambda if you feel like it. I mean, I have no objections actually. Okay? So again, okay, good question. Do you write cons? Okay? My answer to you is I don't care, right? This is the contract. Alright? You feel shook, you want to write in lambdas, you carry on. Can be done? Can it be done? Can be done. Okay? Lambdas can be used to store data. It's true, okay? May not be the most efficient way of doing it, but it can be done, because you can actually use lambdas to simulate cons, right? So obviously you use lambdas to do this, if you want to do it. If you don't use lambdas, you carry on, okay? I have no objections. Do it for kicks, do it for practice, and I'll see you on Friday. Thank you very much. Check the scheme menu. Okay. Before you said you shouldn't use define begin block, right? In what? Define begin block. Yeah, you shouldn't. Yeah, but actually it works. Yeah. No, sometimes it doesn't work. I know why it doesn't work. Okay. Yeah. And also this one, if you use define the last block, it does not work. Yeah, correct. So I don't exactly know when it works, when it doesn't work. So you shouldn't use it. Okay. Because it's very unnatural to use that way anyway. Okay.